Okay, problem 5 is where we have these particles set up 1, 2, and 4. And so I think, right, let's see, 1 has 5 nanocoulombs, and 2 is negative 5 nanocoulombs. 4 is an unknown charge. The distance, the horizontal distance, is 4 millimeters, and 4 millimeters, and then 3 millimeters vertically. And so we want to find where to put an 8 nanocoulomb charge so that the net electrostatic force on 4 is 0. So particle 3 is plus 8 nanocoulombs. Where do we put it so the electrostatic force on 4 is 0? And this is actually easier than you might think. So this is sort of leading us into the idea of electric fields, which we study in the next unit. But when we ask a question like this, where we say, place particle 3 so that particle 4 has 0 net force on it, 0 net electrostatic force on it, and we don't tell you what particle 4 is or what the charge on particle 4 is, and then it is understood to mean that it should work for any particle 4 charge. So we do not know what the charge on 4 is. But the good news is you can just, if you want to do it numerically, and you've got all numbers here, the easiest thing to do is just pick a value for 4. So I'm just going to say charge on 4 is 1 nanocoulomb. Yes, I'm just saying that. And the answer we get for this will work for any value of charge on 4, because if, say, the charge on 4 is doubled, then all of the forces on 4 will double, and they'll still cancel out to 0, etc. Okay, so one question we need to answer here is, what is the distance between 4 and 1 and 4 and 2? And if you do your old Pythagorean theorem, you will find that both of those distances are 5 millimeters. Okay, so the magnitude of the force that 1 exerts on 4 is equal to the magnitude of the force that 2 exerts on 4, because they both have the same magnitude of charge, right? And they're both the same distance away from 4. So that's going to be 5 nanocoulombs. Actually, sorry, hold on. Okay, so that's going to be K times 5 nanocoulombs times 1 nanocoulomb over 5 millimeters squared. And so that will come out to be, let's see, K is 9 times 10 to the 9, and a nano is 10 to the minus 9. Let me get, so let's see, we get a minus 18 up here and a plus 9 on this, and then 2 millis counts as a plus 6. So I think what we're going to get is, I believe, 1.8 millinewtons. Does that feel right? No. Wait a minute. Yes. Yes, it does. Uh-huh. Yes. Okay, I'm satisfied. 1.8 millinewtons. Yeah. Okay. If I'm wrong, so help me, I'm screwed. Okay. So that's the magnitude of the forces from the two of them. Now let's do a free body diagram and see which direction they go. Remember that we're doing a free body diagram on 4. So here's our charge 4. So FBD on 4. And we are assuming that 4 is a positive charge of 1 nanocoulomb. So what we do there is we have, this is the force from 1 on 4, and because that is repelled by charge 1, right? So it's going to go that way, and then it's going to be attracted to charge 2, so you're going to get force of 2 on, that's a 2, sorry, 2 on 4 is going to go like that. So we need to find how these guys add up. Now, as you recall, oh, not that, sorry. That was my fault, actually, I hit the wrong thing. Come on. Okay, let's go for, ooh, how about green? Okay, so we'll go for this. And remember, this angle here is going to be equal to this angle here, because these are just, if you look at the geometry, it's the same geometry, because the angles are the same. It's all, I set it up so that they both have the same angle, you know, from horizontal to forces. All we really need to do is worry about the x component of these, because the y component, since these two have the same magnitude, the y components will cancel out. So the net force in the x direction is going to be f of 1 on 4 times cosine of theta plus f of 2 on 4 times cosine of theta, which is, of course, then going to be just, since the magnitudes of the two forces are the same, we just showed that up here. So that's going to equal 2 times 1.8 millinewtons. And then the cosine of theta, well, theta, remember this little triangle here we have, this was 3 millimeters, this was 4 millimeters, and the hypotenuse was 5 millimeters, so the cosine is 0.8. So, boy, I hope this is right. Well, in for a penny, in for a pound, as they say. Okay, so let's see, 1.6 to 1.8 is, oh, help me, let's see, 1.6 to 1.8 is going to be 2.88. So the total, what are you doing? Okay, what are you doing? Okay, hopefully, oh, no, this one. Okay, so this is going to be, come on, what the hell? Okay, no, stop. All right, 2.88 millinewtons, okay? And it's going to be going directly that way. So now, let's see, charge 3, particle 3 has a charge of 8 nanocoulombs. So we need for particle 3 to exert a force going that way. So this needs to be with the force of 3 on 4. And the force of 3 on 4 needs to be 2.88 millinewtons. Okay, so that has to equal K, which is 9 times 10 to the 9, times our 8 nanocoulombs for particle 3, times our 1 nanocoulomb for particle 4. Again, that's just the value we took to make it work, and divided by r squared. So if we solve this for r squared, that will tell us how far away charge 3 needs to be from charge 4. Oh boy, let's hope so. Let's see, clear, okay. 0.00288 divided by 8e negative 9 divided by 1e negative 9, and then we gotta divide that by also by 9e9, and the answer is 4. Oh, right. So I hope that's right. So that what that gets us then is 1 over r squared equals 4 times 10 to the 4th 1 over square meters. And so we just square rootify that, and we get 200 1 over meters, which means when we invert it, I should be able to do this in my head, but I can't. We should get then that it has to be 5 millimeters away. So the proper placement is, here's 1, here's 4, here is 2, and 3 should be right about over here. So it should be horizontally over from 4 at a distance of 5 millimeters, because then, let's assume, and we can assume this without, you know, screwing ourselves up, we assume that 4 has a positive charge, then 1 is positive, so it's going to exert a force that way. That's the force from 1. 2 is negative, so it's going to exert a force that way. And then 3 is going to exert a force that way. And these would add up to 0 then if you placed 3 5 millimeters to the right of 4. And then for part B of this problem, it's not very hard. because the magnitude of the force stays the same. The only thing that changes with part B is the sign of particle 3. Sorry, I think I'm coming down with something, so I'm getting a little loogie here. But for part B, so this is part A over here, doing like that. For part B, it's the same thing, except you're on the other side, because the only thing that's changed is that 3 now attracts 4, whereas in part A it repelled. Stop it! But everything else stays the same, so that's all that changes there. Okay, that's it for problem 5.